Okay, it's a pleasure to be the first lecture of this morning, of this week. And I'd like to thank the organizer for the tremendous job they did to organize such a trimester in Bonn. So is that good? So I'd like to speak on the triple and connection with Toeplitz operator. And it's a collaboration with Cyril Lévy, who is now in Albi in France, Kevin Fock, who works in Marseille, and Miroslav Englis in Prague. And well, my motivation is just to study non-commutative geometry within the setting of manifold with boundaries, can be important for physics. Within this type of manifold, you have the complex domain. Okay, and then I would like to end up with some application to the so-called Berezin-Toeplitz quantization. So, well, all these topics you could see as totally different, even if there are connections. So today, I want you to join me in the kind of personal journey within this field. So, of course, it's totally arbitrary. So, what can be said about manifold with boundaries in non-commutative framework approach? So you start with M, compact manifold with boundary, some dimension. So you can always see M as a submanifold of its double, so which is still a compact manifold without boundary. And then, of course, you put some vector bundle above this M tilde. So when you see a tilde, this means that you have no boundary. When you see no tilde, you have a boundary. Okay? So you have two natural operators. It's a closure, sorry. So the closure means you include the boundary as a set. Sorry. And, oh, yeah. Okay. Yeah, you have a bar. So you have two natural operators here. Namely, you can restrict, quite easy operation, or you can, by brute force, extend everything by 0 when you are outside M. So, for instance, when you have a pseudo-differential operator on this bundle A tilde, then you can see it as something working at the level at the bottom, so on M, by its truncation. Namely, you first enlarge, you apply P, and then you restrict, okay? This is defined on E, which is just a restriction over M of this bundle. And then you enter in the world of Boutet and Monvel pseudo-differential calculus. You have a lot of different calculi, but this one is interesting because you have this kind of transmission property, which means that this truncation preserves everything, smoothness, up to boundary. And Boutet and Monvel has proved that well, so differential operators satisfy this condition. So, oops, sorry. So, okay, now I would like to make some spectral triple with this type of object. So, you start with a pseudo for the 1 over the E tilde. And, of course, you have to pay attention to the boundary. So you have a trace operator, which is a trace operator. It's just a restriction of what happened just on the boundary. Okay? And you have to realize your system of this P and T on some Hilbert space. So you will choose a realization, which is nothing else than truncation, on a certain domain, of course, which are the, for instance, in this case, a Sobolev space on the closure. And, of course, you want for this section to be 0 according to this restriction on the boundary. And then you have to choose some, this is going to be your operator D, the spectral triple, and A is your kind of algebra. So you choose a smooth function defined everywhere, including the boundary, which preserves all the domain of all powers of operator. Okay? And this is because you know that there is a tension when you want to get a spectral triple between the operator which defines the metric and the algebra. There is some difficulty. You want bounded commutators, for instance. So with Cyril Lévy, we proved 3 years ago that if you start with a pseudo-order 1, so you can think about kind of Dirac, which is symmetric, well, you want to end up with something which is self-adjoint, with this transmission condition, and such that this couple is an elliptic pseudo-differential boundary operator, then, while modulo some restriction on your normal operator here, and of course the fact that this operator is self-adjoint, then you end up with a spectral triple with spectral dimension D. And that's interesting because it covers all situations with a kind of classical, by this I mean some commutative algebra. And well, you can get regularity, for instance, if P is a differential operator, like Dirac, okay, such that, well, technical restriction here. So, well, different people have worked on that. Here is a few lists of people interested by connection, real connection with non-commutative geometry. And in particular, they were interested by, the so-called Boutet-Monvel algebra, the technical difficulties linked with the Wojcicki residue and Dix matrices and things like that. And actually, Jean-Marie Lescure was the first one to exhibit really a spectral triple, a real one, with all full-field axioms, which was regular, for manifolds with a special type of singularity. This means that when you enter this world of singularities, well, you have to work. So this has some physical application. For instance, Shamseddin and Cohn show the influence on quantum gravity of the boundary terms on the spectral action, which is the kind of exercise you have just to turn the crank of the Gilkey's machinery. I mean, you are in the commutative things, or almost commutative, so it's quite easy. And, well, you have paper by Wang, and with Cyril Lévy and Dmitry Vassilevich, we actually wrote spectral action in general case when M has the boundary, and even in the case of you have torsion. So, okay, so now a special type of domain with boundary. Of course, you think immediately about the disk, unit disk, okay, or the unit ball in Cn, the boundary is just a sphere, okay, nice object. So when you think about this, you immediately realize that previous answer was for real manifolds. So what about the complex structure? What about the Cauchy-Riemann geometry, which is behind this, okay? And of course, I also want some extension to non-commutative algebras, not only for commutative. Everything before was commutative or almost commutative. You just to take the tensor product with matrices, so peanuts. So, well, few people were interested by this. In particular, paper interesting here by Alan Klimek and Wojcikowski, where they considered unit disk, and the algebra was the usual Toeplitz algebra generated by the shifts, and as D, they use some kind of equivalent of the derivation with respect to Z bar, and they were also forced to use a kind of Atiyah-Patodi-Zinger boundary condition, okay? Because, well, this is a global type of condition, so in physics you have to choose between local or global, so this is quite important for physics. But I don't want to enter into this because I want to do something completely different. So here you enter the world of complex geometry given by the bounded pseudoconvex domain. So omega from now is an output bounded domain in Cn with smooth boundary, just to avoid complexities. And we assume that omega is strictly pseudoconvex. What does that mean? It means that you have some defining function on omega. What it is, it's just a smooth function everywhere, including the boundary, positively valued, such that in the interior is strictly positive. it's 0 on the boundary, but not vanishing too quickly, so its gradient on the boundary is not 0. Okay? And then strictly pseudoconvex means that you have the Hessian of this function R, which gives you a matrix, is a strictly positive definite metric on Cn. And this is because we have in mind, of course, a Kähler metric and things like that. So just to feel comfortable, just look at the unit disk. So the boundary is just circle. And for R, just take 1 minus the absolute value square. You can check mentally quickly that this is true, trivially. Okay? So in this type of work, you divide the exterior differential in two parts, the holomorphic and anti-holomorphic part, where D is referred to the derivation with respect to Z and D bar with respect to Z bar. And one of the consequences of the strict pseudoconvexity is that, well, you have this function eta, which is just this one form, take the imaginary part, restrict on the boundary. Then this is a contact 1/4. It's a fact. Okay, what it is? Well, this means that eta, exterior product with its differential at the right power, is just a volume form on the boundary. So this gives you, you start with a domain with R, and you end up with something which is a kind of metric on the boundary, if you want. So I need to define the Bergman spaces, so with weight. So for me, a weight will be a multiplication of my function R, defining function to the power of something, some integer, some real number. And G will be a smooth function everywhere, including the boundary, which is strictly positive. I want this to be a weight. Okay? And the Bergman space are the L2 function with respect to this weight. Mu is here just a big measure, which are holomorphic inside the domain. Okay? So you can check that is Hilbert subspace of usual L2. And this means that you have a projection between this Hilbert space and this subspace. Okay? And when W is just 1, I simply forget it. So again, example, take the unit ball. Okay, open unit ball. Take as defining function previous one minus the norm to the square. And take for W just R to some power. Okay? Then this is an Hilbert space. And you have a basis, and what this basis functions should be holomorphic, so this is just, monomial. Alpha is just a multi-index with some coefficients just to guarantee that things are orthonormal. Okay? So quite simple. So, and now I have to define the two objects I had before, namely extension and restriction. Okay? But here, instead of extending just by brute force, I will use this Poisson operator, which is quite nice, because it answers to the question how to get harmonic extension which solves the Dirichlet problem. Namely, you start with a function on the boundary. You want an extension inside. Okay, and of course you want that this extension has the same value in the boundary than the original function, and which is of Laplacian 0. Okay, Laplacian here is a complex Laplacian. Okay, this exists. This is the usual Poisson operator on the disk. And well, it's not trivial, but it's true that K maps smooth function on the boundary to smooth function everywhere, which are of course harmonic. So you extend this operator as an operator on Hilbert space. Okay, and then you do something strange. Or maybe not so strange. K is an extension. So the idea is you extend, you change the metric by some positive function W, and then K star you go back, you pull back. Okay, this is something interesting because, well, Boutet and Monvel proved that this operator, which is of course self-adjoint, is actually a real pseudo-differential operator, which is moreover elliptic, and has a certain order, which is here. So if it's less than 0, you know that the operator is compact, for instance. And it has a principal symbol, which is written here. Well, the formula has no importance. It is here just to show you that you are in a world when you can compute. Everything is computable. That's if you are clever enough, of course. And now I have to do, this is my extension operator, and I have to have the same process, namely the restriction one. So as a restriction one, it's natural to take k star, go back, but you multiply by this, the inverse of this pseudo. Remember, it is elliptic, so the inverse makes sense. And it goes from the L2 of the interior on the L2 of the boundary. Okay? And this is a nice object because gamma k is just 1. And the opposite direction is not 1, but just a projection on the harmonic part. So gamma is a left inverse of k, and it has a continuous extension. You could push it to the Sobolev spaces on the interior, or Sobolev space of a certain order, and it maps to Sobolev space on the boundary, shift by 1/2. This 1/2 is a signature of boundary problems. And k, same thing, but it's shift by +1/2. Here you have to be careful because, well, k and gamma are not pseudo-differential operators. They are only Fourier integral operators. So they look the same, but they are not the same. I mean, technically, it's totally different. So now I also have to define the RD space. What is the RD space? It's just a set of functions on the boundary, so RD concerns the boundary, which have holomorphic extension inside, okay, with respect to k. Again, this is Hilbert's subspace of the total Hilbert space. This means you have a projection between this L2 on this sub-Hilbert space. And this is a Seeger projection, the name of this projection. And now we can define the Toeplitz operator finally. So, is that okay? Well, it's the first lecture, so you can sleep a bit. Okay, take a smooth function on the boundary. Okay, a Toeplitz operator will go from the RD space on the boundary to itself. What it is, you multiply by u. But u is an arbitrary function, so you destroy holomorphy. All right, so you are obliged to project on the holomorphic part just to end up in this space. Okay? And you can do the same for now a function defined everywhere, smooth enough, everywhere. And the Toeplitz goes from Bergman to Bergman. It's the same. You first multiply by f. Again, you destroy type of holomorphic things, so you project. Okay? And for both these spaces, so you start from the classical world of functions, and you are, via this Toeplitz, you are in the, say, boundary operators. So this map is always linear. It maps the constant function to the operator 1, so you always have units around. Okay? The adjoint of t is just associated to the Toeplitz of the complex conjugate of the function. And you control the norm of your operator just by the supremum norm of your function. Okay? So now I would like to generalize, actually not me, it was made by Boutet and Monvel alone first, then by Guillemin, and then both. We introduced, well, a long time ago, more than 20 years ago, the fact that instead of multiplying by a function, well, not to multiply by a pseudo-differential operator and then to restrict. Quite natural. So you start with a pseudo-differential of a certain order on the boundary. Okay? And then you define a generalized Toeplitz operator by something which goes from H2 to H2. Of course, it has a domain, which is first you apply P, so this explains why you have a domain, and you restrict. Why not? Okay, this is quite natural. Or if you prefer, you can define it like this. If you are interested by self-adjointness, it's better to symmetrize things. But here you have to be careful because, of course, the map from the pseudo to the set of Toeplitz, generalized Toeplitz, is of course not injective. In a way, you have to take care of this. So this is where things are delicate, and you are obliged, or at least Boutet and Monvel found this solution, to look at this half-line bundle. Namely, you look at the cotangent space of your boundary, where x prime is the boundary, and you remember this one form, this contact one form from the beginning, given by the defining function, where you are authorized just to dilate it. So this is a half-line bundle. And what the interest of this strange object is that the principal symbol of P is a pseudo, restrict to sigma determine uniquely this type of application, if you want. So you can define the order of the generalized Toeplitz operator as the infimum of all orders of all real pseudo on the boundary with the same Toeplitz. Well, this makes sense. And then you can define the symbol of a generalized Toeplitz as a symbol of Q. Q is the pseudo. Restrict on this bundle for all Q's with the same Toeplitz and same order. Yeah. 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 So it's always. Yeah, this is more or less the idea. Yeah, but it's. Yeah, this is the point. So I'm coming to this now. Yeah, well, that's a tricky point. And the trick is the following. Precisely for any generalized Toeplitz, they always exist some real pseudo on the boundary with the same Toeplitz and which commute with Q. This is just by abstract nonsense. So you know, if you commute with this projection, everything, life is easy because well, you have nothing to do. So in particular, takes the product of two generalized Toeplitz. So you replace TP by TQ, which is here. Applied definition is just P times P prime, P times Q. You commute, and this is by definition the Toeplitz associated to the product. The product of two pseudo is a pseudo. So this means that you have proved that they form an algebra, which is a key point. Okay? And of course, everything has been cooked well, precisely. So the order of the product is just the sum of the order. The symbol of the product is just the sum. You can speak about elliptic GTOs and so on. Okay? So in the Guillemin's word, this means that pseudo-differential operators are just generalized Toeplitz operators in disguise. So when you look at this, you say, oh no, come on, that's the other way around. You start with a pseudo, and then you construct Toeplitz. Well, after some experience, I guess that Guillemin is right. I mean, this is the right way to think about it. I don't know if you agree, but well, I think it's correct. Okay, so now we have to make a link. So there's a link between the boundary and the interior. Okay, so you have some kind of identification process, namely for any Toeplitz associated to a function on the Bergman space, you can define a generalized Toeplitz on RD space on the boundary via this operation of extension restriction. Okay, so you have two Hilbert spaces, H2 and A2. They are separable, so you have a unitary from one to the other. This unitary is explicitly written here. So you have, of course, the extension, but you have this strange object, which is the square root of the Toeplitz associated to the real pseudo that I defined before. And when TF is defined on the Bergman space, so first you extend, you apply TF, and then you restrict. And if this is actually equivalent to the multiplication of two Toeplitz. Okay, so it's a generalized Toeplitz operator. Of course, you have a domain, but maybe it's not so important. So the theorem we got is the following. As AH for RD, the algebra of all generalized Toeplitz operator of negative order. For Hilbert space, you take the RD space on the boundary. And for D, you take any self-adjoint elliptic generalized Toeplitz operator of order 1 on H. Then this triplet is actually a regular spectral triple of spectral dimension n, which is dimension of the domain. Okay? And in the Bergman space, you have the same kind of result. So B for Bergman. You take the algebra generated by the usual Toeplitz operator, multiplication by functions. Okay, smooth enough everywhere. H is just the Bergman space. And D, well, you choose a self-adjoint elliptic generalized operator of order 1 on the boundary, and you pull it back on the Bergman space. Okay? And then again, this is a regular spectral with the appropriate dimension. So recently, Kevin Fock has improved a little bit this result using not only the GTOs, classical GTOs, but with GTOs which have an asymptotic expansion in homogeneous part, which can have some logarithmic symbol in it. Okay? The only restriction in this long way to phrase it, well, let's say that the principal symbol has no log term. Okay? And it makes sense. And what's the interest of this? The interest is that, well, when you want to get a nice defining function, because you have plenty, well, you could try to solve the Monge-Ampère equation, namely to find some function which is, again, 0 on the boundary with gradient non-zero, such that the G of U is just 1 in the interior, where G is just the determinant of this matrix when you can see the appearance of U, Laplacian, and the behavior with respect to D and D bar. And the interest of this approach is that when you start with a strictly pseudoconvex domain, then you can prove the existence and uniqueness of U, and this U is not smooth at the boundary. So U, in some equivalence, has some logarithmic term in it. Okay, so this is why this has been proved by Lee and Melrose. Is interesting to this generalization. And this equivalence means that the difference between U and unitruncated series is a smooth function which vanish at certain order. This technical point. So, okay, now we have an example of spectral triples based on the algebra of Toeplitz operator on generalized strictly pseudoconvex domain. I would like to go a little bit in physics, well, mathematical physics, say, and to use the Fock space, which is here defined, the L2 function defined on Cn, so not bounded, with respect to some Gaussian measure. Here, d mu is the Lebesgue measure. And what is the interest of this Fock space here? The interest is that you have the so-called Siegel-Barman transform from L2 for n, with respect to the Lebesgue measure, onto this Fock space, which is explicitly written here. Again, the formula has no real importance, but it's just integral, so if you know f, you can compute. Okay, that's it. And this is a unitary map between this Hilbert space and this one, explicitly. And this Siegel-Barman transform make a link between function on R n onto to function on Cn. Cn is R2n, okay? But you restrict to holomorphic function, okay? That's the idea. And this, yeah. I will also use the Heisenberg group. So quickly, the Heisenberg group is just Rn cross R, where you have Qp and T, the three variables. So you add the vectors and you add the numbers, but you twist with some symplectic part of Rn. And then it's well known that this group has generator. Let's call it capital Q, capital P, and T. For its Lie algebra, and the only non-zero commutation relation are well known, written here. Okay, and all of these are related because, of course, you have the famous Schrödinger representation of this Lie algebra of the Heisenberg group on this L2 space of Rn, where the Q's are mapped on the multiplication by the variable, let's call it x. The P's are mapped on the derivation with respect to x. Okay, minus I is just to be self-adjoint. And the T is just the multiplication by I. You know this famous I that you have in the quantum Heisenberg relation, which makes a huge difference. So, of course, when you have a representation just changing your Hilbert space, you could shift this representation to the Fock representation, let's call it nu, on the Fock space, just by some Siegel-Barman transform, or on the Bergman space, again by operator which are naturally defined. You have a seat here, please. Okay, good. You are young enough. Yeah, that's fine. May I sit? Okay, so what's the interest? Richard Hove proved, well, 24 years ago, a nice... Sorry? Sorry. Nevertheless, it's an old result. So, well, you know, there is prescription. And, well, this isomorphic is interesting for us because, you know, this is an isomorphism between pseudo-differential on Rk, usual one, of certain order, to the Toeplitz operator on the Bergman space on the unit ball. Okay, but here you have half order. And half order is strange because, you know, it's related to the fact that you have to be careful. You go from the non-compact Rn to the compact unit ball of Cn. Okay, so a lot of traps behind this type of result. So, for instance, if you want Dirac-like operator on this Bergman space or this space, well, you have just to mimic the usual construction. For instance, the usual Dirac operator is just based on this gamma mu d mu, standard on Rn. And using the previous maps, you can just shift this ID, or you replace minus I dx mu by p mu. You take the RD representation that I gave before, and just via the nice unitary map, you keep gamma mu that you have here. You have create room enough just to turn around on the fiber. And what you have done here, you can do the same for the Bergman space, okay? Just by shifting everything. So the natural classical spectral triple on the unit ball are something like this. You start with the algebra of usual Toeplitz operator associated to smooth function on the sphere, okay? Acting on the RD space of the sphere, and previous operator. Then this is a regular spectral triple of dimension 2n, okay? And you can do the same for the algebra of Toeplitz, sorry, defined on the closure of the unit ball, acting on the Bergman space of the unit ball. And again, previous operator give you the same result, which is the same techniques. So just to say a few words, I don't know if I have time. Well, to compute the dimension, you have to compute the spectral dimension. Okay, so you have to enter the world of Dixmuir traces or these single traces. So here, when you have a GTO on the generalized Toeplitz operator on the boundary, which has as order minus the dimension of the domain, then you can show that it's always measurable, okay, in cone sense or in let's say the Australian sense, which is Dixmuir traceable. And what is this Dixmuir trace? Well, it's what you expect, namely it's the integral of its symbol. For respect, this element is the boundary. This is one form, the contact one form what you had before, and the volume form defined by the defining function what you have. So everything was in your hand from the beginning, actually. And it's amazing to see that this is independent of the defining function R. Well, in general, in non-commutative geometry, you have to compute such a thing for an element in the algebra, and well, we have formulas for this. I don't want to enter the details, but it's possible applying the machinery. And these people have extended this type of result computation of Dixmuir traces for Henkel operators. What are the Henkel operators? They are operators which are same as before, but you multiply first by a function, and you project on the complementary part of the holomorphic function. Yeah, thank you. And, well, okay, you have formulas, an extension to different generalized Siegel-Barman Fock space. You know, it's an industry for complex people. So now I would like to do something different. So actually, this was my original motivation, just to understand what is a Berezin-Toeplitz quantization. So these Berezin and Toeplitz techniques have some interest, for instance, in classical geometry, where you can see the appearance of Kähler manifold, like for instance in phase space manifolds. And it was a motivation of Berezin to study this geometry quantization on Kähler manifolds. For instance, for the spherical pendulum, you get a complex projective space. But also in quantization, where both the, let's say, the geometric and the deformation quantization gives the correct semi-classical limit. You have to be sure of that. And it has been made by Bergman, Meinong-Renken, and Schlichen-Meyer 20 years ago. I will come back at this point in a moment. You know, you always have these two different quantization, geometric and deformation, say star product. And Berezin-Toeplitz is a kind of mixture of both. I mean, a kind of link between the two. And another work by Anderson, not a work, it's a program actually, where you want to consider quantized spaces which are more or less moduli spaces of flat Riemannians on some surface, things like that. And also, the Berezin-Toeplitz quantization has some implication on the notion of fuzzy manifolds, Amador, which has been considered by Grosse Steinecke. But the question I would like to address today is the following. Is Berezin-Toeplitz quantization part of non-commutative geometry? And by this I mean just to produce a spectral triple, which is the ordinary standard paradigm for non-commutative geometry. So for the Montreal quantization, 10 years ago with Victor and Garcia Bondia and Varili, we proved that the answer is yes. So I'd like to consider this case now. So the problem is just to get a spectral triple related to some kind of Berezin-Toeplitz star product. We need something like that on omega. And omega is still an open, bounded, strictly pseudoconvex domain. well, smooth boundary just to be on the safe side. Okay? So what is the idea? The idea is just to glue spectral triples with different weights into a single one. We'll explain in a moment why. To get an answer to this problem. So, but I need some technical ingredients, which are, well, I exchange the original defining function to its inverse, to its log, why not? And I get this metric, which is actually a Keller metric according to the definition of strict pseudoconvexity. Take the determinant, you multiply by this. It's kind of artificial, so I don't want to enter in this detail. And now take any smooth function defined everywhere, including the boundary, which is strictly positive inside. And we know how to build Bergman space associated to weights. So for weight, I will label this weight by integers, namely Wn would be my weight. So it's my function g, defined before, based on the defining function, times r, still the defining function raised to some power, which is integer. And you glue together all these Bergman spaces. Okay, so you have several floors. And for any function defined everywhere, you define a kind of T plus operator. T plus is a Toeplitz acting at each floor. Okay, this makes sense. I gave a definition before. And as an algebra, I will use the algebra generated by all these T plus Toeplitz operators. Okay, so you recollect everything with different floors. And as in the talk of Adam last week, I will use a number operator, namely this is just level of the floor, just a bit, this is technical. N is just dimension, so this is a constant, times the projection on the nth element. So, and now the key point is the following. The product of two Toeplitz, T plus, is not a T plus operator, but it's almost a T plus. Okay? So this is equivalent to a sum of T plus operator times the inverse of this level, say, number operator. This has been made by these three people, as I explained. And in this sum, you have different terms. The first term is just given by the original classical product. The second term, when you make difference, is given by the Poisson product. And this is, by definition, the existence of a star product. Okay, this is definition. So you get a star product for this domain equipped with this metric, which is defined by this function here, defined by this differential bilinear operator. And H is just the inverse of N, so it's at each level, so it's a discretized H bar, if you want. And while this star product has interesting properties, for instance, the product of two is just the original product if G is holomorphic or F is anti-holomorphic. And of course, you realize the program of real quantification, namely T of V star product is a product of the two T's. Okay? So you have pulled back the product of two T's via the T plus minus 1 in a way. Okay? So here, this equivalence is important. It means that, well, you can decompose an operator in a sum like that, where F are smooth functions. This means that you control the difference between the original B and the truncated sum, okay, at each level. It is controlled by something that is, well, totally under control. Okay. So now you apply something which is standard in complex analysis. You will add one dimension, so you will take the unit disk bundle over E. So you start with the original domain. So Z is in omega. T is an extra number, complex number. That's but you have this restriction. So we define omega tilde. It is strange, but the interest is that you can prove that this is a strictly pseudo-convex domain for R tilde, which is just difference of R and the absolute value of T squared, which appear here. And then you have to test the crank from the beginning. I will not do it for you. So from the beginning, you have to construct the extension operator, K tilde, and so on and so forth. And so since any function on the boundary, everything including the boundary, can be seen as a function on the boundary of this set, this extension via all this tilde operation correspond to this T plus. You can prove that this kind of equivalence. And we have the result. Namely, it takes the algebra generated by all T plus operator for any smooth function on your domain. As Hilbert space, you take the recollection of all these floors, okay, Bergman space. And for D, you take, well, this lambda tilde pseudo-differential operator from the beginning. You take the GTOs associated with pseudo, okay. You tilde this, well, turn the trunk, take the inverse, it's order 1, and then you can show that this is a regular spectral triple, okay. So if you think in terms of formal power series, then A is nothing else than the formal series generated by all these T plus operator. Okay. So finally, if the question is Berezin-Toeplitz quantization part of the non-commutative geometry, the answer is yes. In the bucket. Thank you. No, the idea is just to show, there is this problem of quantization because you have a lot of quantization. Well, we know that you can forget about quantization. Take the Schrödinger equation and solve it. You push just the key button on your computer and you solve the second order differential equation and that's it. Forget about this stuff. But if at the conceptual level, if you want to understand why we have so many quantization, why this quantization could play a role, the first thing you have to do is just suppress the complex entries of it, because at the end, the quantization should not depend on the complex structure you have chosen. So the idea is just to work on the set of all possible complex structure you can put. So this is a base space. As a fiber, you put all this machinery. On this, you made a connection, so a kind of etching connection, okay? And then you get something which is, with many hypotheses, you get something which is independent. So, first step. Second step will be to understand all this complex analysis, because here I've just scratched the surface. Then you have to put some singularities on the boundary and so on and so forth, and then, well, it's another stuff. You see, it's a program, actually. Yeah?
Two short questions. First, what is the geometric meaning? Can you say something about what spectral is? What's the geometric meaning? What's the, let's say, do they give something like a homology class?
I have not checked that the K-homology class is trivial. I'm sure it's not, but okay, it's just a bet. Okay, okay. Second question is?
Second short question. From the construction, it looks like the inverse of the Dirac operator is in your algebra.
Yeah, that's right. This is just pseudo-differential operator. But now you could turn around and to find different kind of operators. This is also another project. But, well, okay. If you want to join the club, you're welcome. No, I have no answer. You're right. It's a fight between organizers. So. Yeah. Probably. Yeah, so, yeah. Well, you know, as far as star product is concerned, there always exists a kind of transformation from one star product to another one. So in this respect, this result is not surprising. But, you know, spectral geometry is much more involved. You have to produce a Dirac and a nice one. And, yeah. Yeah, yeah, but this is in speed of deformation, quantization. You know, yeah, this Berezin is a kind of yeah, and geometry. This is the interest. Yeah. So. Yeah, of course, because we are more or less in pseudo. I agree. So you have to work. I agree. Something new? No, because more or less you have mimic, you know, the original stuff. I mean, technically it's much more difficult, but I don't see why you are worried about this, because I agree. This is why, you know, this trick of Boutet and Monvel just to restrict to the appropriate bundle this is where you could see this in action, in practice. You can touch difficulty. Yeah, it preserves all the domain and so on. Yeah, that's right, yeah. Sorry, I should have said this. I agree. This is where there is a trap. So, but, well, you know, this is the open unit ball. So just forget about the dimension. Just look at the disk. Actually, even for the disk, we don't have a nice geometry for the disk. I mean, the non-commutative one. I mean, okay, this is open. So as far as Poincaré half plane or unit disk is concerned, I don't think we have definite answer. I have not invented it. It was done before. But, well. Yeah, but this is quite important technically.